Okay, croeso. Thank you, ladies and gentlemen. Thank you for coming to the final session of today in the Inspire stage. It's Understanding Quantum. Now, I'm not going to tell you anything about it because I have no idea what it is. So this discussion will introduce you to the rapidly developing field of quantum technology. So chairing this discussion is Anke Lohmann, the founder of Anchored In. It's an innovation consultancy as she connects research, innovation and industry to support commercialization and specializes, of course, in quantum technologies and photonics. So the panel is being recorded about 10 to 5 to 3, sorry, we will be, 4, sorry, we will be asking for some questions. So if you've got any questions, don't be shy, raise your hand and Anke will ask you for some questions about 10 to 4. Otherwise, I will hand you over to the panel and our chair, Anke. Anke.
Thank you, Chris. So, in September, the North Wales Police finished a trial with D-Wave. D-Wave is a quantum computing company, and they were trialing to see if they could optimize their response rate to callouts. The outcome of this trial is that they found that 90%, they could reach 90% of the callouts within their set time. Now, I don't know what at the moment the response rate is, and I don't know what the set time is, but when I spoke to the North Wales Police, they said it was significant. I think, and don't quote me on this, I think they said from 30 minutes to 11 minutes. Now, this is a trial. This is limited to a small number, to a small region. We don't really have enough of quantum computing to make this happen, but I just want to start with that to give you an idea what might be possible with quantum technologies. So you might be aware, I don't know, about 2 billion have been invested in the UK publicly and privately into quantum technologies. More is going to come. So there might be, it's a good time probably to engage and see how that could help you as well in future. Welcome to the panel already, you heard that. It's about understanding quantum technologies. We're not going to understand quantum technologies, but what I want to convey today with the panel, with the excellent panel I have, is what it could mean to people. What are the applications, how it might change what you do in a business. So that's where we're focusing on. My panel, I have 4 people from different organizations with different expertise in quantum technologies. Paul Seeley, he's from the Digital Catapult. Ewan Davis from IQE. Anthony Bennett from Cardiff University. And Zoe Davidson from BT. And these people will help me and help you to explore what quantum technologies actually means. And with that, I would like to start, to ask a first question. And if I maybe start with Paul from the end, is, so please tell me what you do. What does the Digital Catapult do? What do you do in the Digital Catapult? What is your role? And how does this relate to quantum technologies?
Good afternoon, everyone. So my name is Paul Seeley. I'm the Director of Emerging Technology at Digital Catapult, and this includes quantum technologies and AI and others. So just Digital Catapult, you might know us. We're a technology innovation organization focused on the practical application of deep tech. And so what we want to do is to get new deep tech, it could be ideas, technologies, or organizations into the real world and get them adopted by different organizations. And so we work in different areas, but we work on different technologies. We have future networks is a big part of what we do, creative technologies, IoT, AI, of course, and but also quantum technologies is a key area that's growing. We see this as something that's a huge opportunity for the UK, and for that reason we're doing a lot of work to work on innovation activities around that. Yeah, and my role, I'm in the technology function in the research area, and I'm responsible for those different areas to look at the different things that we're going to do with that, the different programs that we want to work on about how we look at particularly adoption of quantum technologies, how we can take these emerging things and get them into the hands of real users to try and experiment with them. And particularly to try and join them together, because I think when you get a real world, someone who understands their business to talk about where a technology can add value. You get something different rather than a technology push. You can get some real insights. And we've seen in the quantum particularly where we can get some new knowledge, actually new knowledge created where someone said, well, this is a real problem, and then you can then adjust the technology to suit. Yeah.
Thank you. And is there any particular example where you say, you know, these are the applications, this is where we see adoption from your conversations?
So we've run a few programs. We're looking at quantum across multiple areas. So quantum networking is something we're interested in. That's much longer term, I'd say, because we've got a future network team. We're interested in quantum sensors. There's some very early stage, some near-term capabilities that are coming through quantum sensors. We've got an IoT team, and so Internet of Things. And in some ways, quantum sensing is like an advanced IoT sensor. And so some of them are sort of available now. So we've got one in our lab that we can use. It's a magnetometer. You can use it for non-destructive testing. So if you've got a crack in a piece of metal, you can identify it through magnetic resonance without actually having to peel open the thing to see whether it has a crack, which obviously breaks it anyway, so that's no help. So that's and in examples in quantum computing. So we've run a couple of programs where we've given people access to quantum computers, and there's a whole suite, and I'll touch on a few later. But some examples. Oh, someone whistling. I always wonder if it was just me. Okay, shall I just carry on going, and then you'll fix it? It's the tannoy, right? Okay.
Okay.
Okay, I'll carry on then. An example, I was thinking, clean energy, offshore renewables is something that's in Wales. Apparently, it's quite complex to design a set of wind turbines where when you've got wind coming, obviously. When you've got wind coming, obviously you've got one turbine. If you have them all in a row, then that means that the ones at the back end don't get as much wind. So ideally, you would have them all stepped off, but wind doesn't go in the same direction. And so a quantum optimization, it's an optimization problem which quantum computers are quite good at, where there's lots of different options, but the system is relatively small. And so that's something that you can solve with a quantum computer to come up with an array of wind turbines that is optimal for the wind in that area, for example.
Okay, thank you. Ewan, same question to you. So, who are you? What is your role? IQE, obviously, I assume people know IQE. And then what do you do in quantum?
Okay. So, good afternoon, everyone. I'm Ewan Davis, IQE Group Technology Director. Now, IQE is a local company, or headquartered locally in Cardiff, and we have a big plant in Newport, so just down the road. We've been around since 1988, and we manufacture compound semiconductor wafers. Now, these are materials which ultimately are manufactured into electronic or photonic devices, and then they'll find their way into modules and systems, into many of the devices and that we have today, whether it be mobile phones, computing, laptops, solar cells, and at the end, the list is endless. Now, in being around for 37 years now, I could say that IQE is being part of the Quantum 1.0 generation of materials and devices, because we were talking there about lasers, transistors, and generally semiconductor devices. Now, I think it's fair to say that the second generation quantum, the more emerging technologies, are more concerned with some of the things that Paul's already mentioned, and I'm sure my colleagues on the left-hand side are going to go on to mention things like timing, positional navigation and timing, imaging, communications, computing, amongst others. And so what IQE is doing today is participating with many collaboration partners within industry and in academia in developing new materials for the second generation quantum technologies. So that's what we're doing, and it's an emerging business for us. Our traditional business is in classical telecommunications, in sensing, but we are now starting to build up a portfolio of materials technologies to service a lot of the new applications that you're going to hear about from the panel here today.
Thank you, Ewan. So, can you hand over to Anthony? Anthony, again, same question to you. You know who you are, who you're working for, what your role is, and how you're involved in quantum technologies.
Sure. So my name's Anthony Bennett. I'm a professor in the School of Engineering at Cardiff University. So I lead a group who work on semiconductor optical quantum technologies. And we're funded by, among other things, Innovate UK and the EPSRC. And one of our bigger projects is that we're part of the UK's quantum computing hub. So this is a very large collaboration, about 20 different universities across the UK, one of the 5 hubs set up by the government to push forward collaboration in quantum technologies. So I should say that before I did that, I worked in industry for about 15 years for Toshiba Research, where I was a team leader in the quantum information group. So my whole career has been about using semiconductor devices that manipulate photons or quanta of light to demonstrate interesting phenomena that we can use in real-world technologies. So the idea here is that the principles of quantum mechanics can be applied to, say, IT systems. And I guess this is a theme that runs through all of what we're doing here today, what we're talking about today. But it is briefly worth mentioning, though it's a bit older than what we're talking about now, that this year it's 100 years since the development of quantum mechanics. So 1925, very significant publications by Heisenberg and talking about different formalisms to describe quantum mechanics, and that is why this year has been designated the International Year of Quantum. And obviously that concept of quantum mechanics is a very hard thing for most people to get their head around, me included, many times. What I would like to say is that over the 100 years, that quantum mechanics has been tested to a very, very rigorous extent, far more so than many other theories that we have about the world around us. And I would argue that it's only in the last 25 years that people have realized that given that quantum mechanics is correct, we can use it for things. So we talk about quantum technology as if it's a monolith. You know, there is a technology which is quantum. It's not. There's so many different ways in which quantum technology could be incorporated into everyday devices, whether that be computers that can solve difficult problems, secure communications networks, or sensors, or many of the other things that have been mentioned already. I think it's a very exciting time to be doing research in this area and seeing these concepts come out of research labs and go into real technologies that will change the way we live our lives. So,
Thank you. And Zoe, the same to you. Same question.
Hi, I'm Zoe Davidson. I'm a technical research manager at BT. I work in the optical and quantum research team. So BT is one of the country's largest telecommunications providers, and we do everything from radio access network, 5G, 4G, things like that, through to fiber, through to at-home business. We sort of touch anything that's using a telecommunications network, we're there. We then kind of replicate that within our research department. So we have, I think at last count, about 100 people or so working in research at BT. And if you can think of something that touches a network, there is somebody researching that at BT. So we have people working in 6G development, in AI, machine learning, optics, quantum. We do the whole lot. So within my team, we're very interested in that optics and quantum space, and specifically what I'm working on is around that quantum network side of things. So we've had a range of research projects in that quantum space. One of my colleagues works in the use of quantum computers. We're not looking at building a quantum computer. There is many very good businesses in the UK looking at that problem and worldwide. BT at the end of the day is a networking company. We don't build computers. We never have. We want to use computers, and that's what we've done, and that's what we want to do. But we also have people looking at quantum sensors, entanglement, quantum key distribution, security, and protecting our customers from the sort of potential threat that is quantum computers on their security. So that's us.
Oh, thank you. And if I just want to come back to the applications. You touched on those applications, but what do you see are core applications for quantum technology? We mentioned computing a little bit, but also communications, networks, why networks? We talked about quantum sensors. What is it they will enable? Who wants to go first? Paul, do you want to go?
Yeah. Yep. Yeah. So we touched on it a little bit. So if we talk about the different types, I think you got quantum computing has the potential. I was going to pick up on the sort of timing wise. So we've had over the past probably 20 years has been a switch to focus from the science to the engineering of all of these devices, and I think we're getting close to the point where quantum computers can be really useful. And do something different to what you can get, or ideally better in certain circumstances compared to what you can get with a classical computer. And over the long term, they should solve problems that are impossible for classical computers to solve. And unfortunately, as you touched on, I think one of the problems that they might solve is cryptography. Which is a bad thing, and therefore there's a whole bunch of pieces of work looking at how to mitigate for that. And so quantum computers use cases are particularly good at optimization, simulation. I think in the life sciences, it's simulation of systems, particularly ones that have a quantum mechanics underlying them. Then that's probably an early type of use case for those. So there's a whole suite of quantum computing things. Quantum sensing, I think they can provide novel capabilities by that. So like gravimeters. There aren't very many gravimeters around, but they tend to be quite bulky. But they can. But there are quantum gravimeters, and they should be able to be shrunk down onto a system on a chip, so that you get kind of like a size and performance. That will take a long time. At the moment, they're still big-ish, I think, the ones that I've seen. So there's a whole suite of other ones. I think some of the use cases particularly interesting around. You mentioned timing. So timing, navigation, gyroscopes, they're all really important quantum sensors, in particular in the time of, they talk about GNSS resilience. So it's Global Navigation System, satellite system, is that what it's said? So it's like GPS. If there's GPS jamming, then you probably want sensors to enable you to get around that, and then you can have a suite of quantum sensors that can help you in that kind of environment.
Yes, so we have a concern. Our concern for our customers and our concern for ourselves in the cryptography side of things is that there's this concept called harvest now, decrypt later, which is where a malicious hacker comes off, taps onto a fiber, reads off all of your data, and they know they can't crack it at the moment, right? If you're using standard cryptography at this point in time, there is not really any computer that can solve it. I think the scale of how long it would take even a supercomputer to solve these algorithms is in the factor of we'd all be dead by the time that happens, so it doesn't really worry us too much. The problem is if you have these quantum computers come along that have these really great abilities to do all these factorial calculations that can then potentially crack this cryptography. And so what we're doing within research, but also wider into BT, is looking at the deployment of technologies like QKD to help protect our customers against these attacks, but also things like PQC, which is this concept called, which is post-quantum cryptography, which in of itself is not a quantum technology because it's still mathematical-based cryptography, but it's a new suite of algorithms that have been approved theoretically to be protected against quantum attacks. So there's definitely that security side of things, but then also, as Paul was saying, when it comes to the optimization side of things, we want to optimize our networks, right? We want our networks to work better, and that's what we were seeing in North Wales with this deployment of these D-Wave annealers in the police, is that if you use something that's really good at optimizing problems, you can build a better network. You can have a network that works better, that's more self-healing, that works better for our customers. And so, yeah, all of those applications of quantum technologies are really useful across the board in our networks.
Thank you. So, Anthony, I'm going to ask you that question. So what misconception do we have about quantum computers, particularly?
Okay,
So I think we need to address that.
yeah, I mean, you could easily generate, give yourself a lot of misconceptions about quantum computers by opening the popular press. So, go and look at the front cover of a newspaper or popular science journals, and you'll see a lot of very exciting front page stories about how a quantum computer has been invented that solves some particular problem very quickly. And some of these results are remarkable from a technical standpoint. But the challenge of making a computer which can be scaled to arbitrary size and programmed and solve problems, generic problems, is very substantial. So what I would argue is that even if we can make a programmable, scalable quantum computer, it may only be useful at solving a very small number of problems. It won't be competing with your desktop PC, and it won't be suitable for solving the sort of problems that maybe AI could tackle. But it can be used for certain things that are really economically valuable. So we talked about breaking the modern cryptography systems. I think we can all guess who might be interested in funding work that would hack into cryptography systems, and there's a lot of money behind that. Another good example is searching large databases. Again, Google is very interested in quantum computing, has put a lot of money into it. And then the other one is probably sort of generic optimization problems, something called the traveling salesman problem, about Amazon have to go and deliver a certain number of parcels to certain addresses. What's the shortest route they can take? That is a problem that a quantum computer is good at solving, better than at solving than a classical computer. So what has been demonstrated so far? If I could highlight one particular example that really drives home maybe the misunderstanding the public has taken away over quantum computing, it's a paper in Science from about 3 years ago which claims quantum supremacy. So quantum supremacy is the point at which a classical computer delivers an answer to a problem faster than any classical computer could. Sorry, I think I said classical. What I mean is a quantum computer now can solve a problem that no classical computer could. Now, this particular computer that was demonstrated consisted of a large number of beams of light going into a very complicated piece of optics, and where photons were detected at the output. And it performs an algorithm which is called boson sampling. Okay, what is boson sampling? Well, exactly. Boson sampling is not useful, and indeed, in the sense that it doesn't generate money for anybody. There's no known practical application of boson sampling. But it is an algorithm that can be used quickly to generate a very exciting result that gets you a paper in a very good journal and gets onto the front page of the newspapers. The big disadvantage of boson sampling is that the actual algorithm is set by the thickness of the pieces of glass used in the experiment. It's not programmable. You take the light, you put it into the piece of glass, you get a result. You couldn't simulate that classically. So that is very interesting from a fundamental computing standpoint, but it's not programmable. So a lot of work going on quantum computing nowadays is tackling these problems where we can get results quickly. We can do something that somebody can't solve. But the really big question that comes after that is how can we make something general purpose, programmable, and scalable that can tackle the hardest problems. And I think maybe the public has not been told the truth about how hard that's going to be. Can I say that? Is that too? Yeah, I think we can say that. I'm an academic. I can comment on the technical aspects. It's allowed.
Okay. Thank you. So I just coming back to, we talked about misconception and how far quantum computers are, but there are some examples where algorithms have been developed as part of a quantum computing, sort of looking into potential applications, which I think have shown other potential positive effects. So there are things that are taking place at the moment that already have an impact that are not necessarily quantum computer, but have been done because of quantum technologies and to explore what can be done with quantum computing. But I want to come back to, just what, in terms of, for whom would be quantum technologies, and this could be sensors, it could be computers, it could be networks, which industry would benefit and what elements, particularly in Wales? I don't know, Paul, do you have some thoughts on that?
I've already touched on which industries. So there's quite a few industries. I'm just thinking about sort of industries that are important to Wales. So advanced manufacturing. I think there's a lot of opportunity in and in defence actually. There's a lot of opportunities for sensors. There's as I mentioned, they're probably quite early, near term. Some of the sensors that are available. I think it's to the point where the sensors. People have the products, but now they need to be, they talk about, in the sensing space, SWaP-C, size, weight, and power, and cost. And so we're at that phase where you've got something that might be a magnetometer, it might be some sort of gyroscope, and then it's get to the right size and shape and cost to be useful. That's in the manufacturing space. So, for example, for things being manufactured, say aerospace, particularly navigation you mentioned, but also in the factory floor, monitoring the systems, quality management, those kind of things. That's really interesting. There's potential optimization across all of those floors as well. If you're logistical optimization, which is it's a kind of like a variant of this traveling salesperson is, or there's algorithms for the network path is effectively the same kind of thing. You could do that in a manufacturing sense to optimize the whole system. So just in that one place, and I mentioned offshore renewables, that's really interesting. FinTech has got doing a lot of work in terms of forecasting. I think quantum computing is particularly interesting for time series forecasting, which doesn't work very well. Classical computers, machine learning algorithms are not so great at time series. Quantum computers are particularly good at them. Fraud detection in fintech as well is their quantum algorithms apparently are particularly good at. Again, I think you were mentioning in terms of finding, searching in terms of it's the same kind of thing. The needle in a haystack problem. That's something that they're particularly good at. That's just some examples, sort of referring to things that might have relevance here.
Thank you. Hyun, is there something you might want to be able to comment?
Yeah. Well, again, we're more the solution providers, I think, at IQE in providing materials that are going to manufacture all of these devices in all of these end-use applications. But, having participated in something in the region of about 16 or 17 government-funded quantum technology projects in the last 10 years, I've had a great insight into all of these end uses. And you've heard them all from the panel today. Certainly, and in Wales, where this might have an impact, of course, is in our own industry, where IQE is part of the compound semiconductor cluster here in Southeast Wales. And, IQE manufactures wafers. We have device fabrication at Vichy. We have semiconductor processing equipment manufacturer in KLA, again in Newport. And over in Caldicot, we have Microchip, who package semiconductor devices. And they are the four core industries of the cluster. We also have great academic partners. Anthony's part of one of those academic partners, and the other one is Swansea, and just down the M4. And we are served by a lot of public bodies as well. We're in a position to solve all of these materials issues in this fantastic emerging technology. And so it would be a huge benefit to the region, in addition to what we're already exploiting through your classical photonics processes and electronics like power electronics, for example. So emerging quantum would have a huge impact on us as a solution providing industry, if you like. But in terms of the end use, I can think of, I mentioned microchip, and Paul also mentioned timing, position, navigation, and timing. I think microchip is out there with one of the smallest swap devices that we have in atomic clocks today. I think it's called the CSAC. And that atomic clocks, you mentioned as well, Paul, GNSS denied environments, right? And these are the exact things that are there to try and prevent, as well, I think we've heard about it a lot in the news in recent months, right? That, you know, planes are being jammed. And I think we're going to have these systems, these small, lightweight systems on aircraft. So, you know, we have a large aircraft manufacturer, at least for the wings anyway, in North East Wales, in Airbus. Microchip is manufacturing these smaller atomic clocks that are going to go a long way towards solving these sort of position, navigation, and timing issues in such environments. And certainly, you know, in and around Wales and the UK in general, we've been part of projects which I don't think we've mentioned it so far today, but we've mentioned quantum sensing. But we were part of some very exciting projects in LiDAR technologies, which we were working with end users in automotive, in rail infrastructure, and in defense, not surprisingly. And we were looking at technologies which could detect objects in all sorts of environments and through all sorts of obscurants, and eye-safe technologies as well, so laser technologies which were eye-safe. I think we had a specification provided to us as a consortium for automotive requirements that ultimately the system would need to detect a brick from 300 meters for a car traveling at 70 miles an hour on a motorway. So tremendously exciting stuff, and through all sorts of fog, snow, and so on. So really great to be part of those systems. And you know, we were in there with the end users as well, large British manufacturers of vehicles and Network Rail as well, looking at the stability of cuttings in the rail network, for example. So we haven't mentioned LiDAR so far today, so I thought I'd put that one in as well.
Thank you. I just have a question. Does anybody from the audience want to ask something? Because you're over there. Could you? Thank you.
You've described, it sounds like we're not going to be using quantum computing for everything. There's going to be some very specific use cases. Will they ever be manufactured in the sort of quantities we tend to think of as computers? Or will they be like 1,000 sitting in universities? I mean, are they going to be, when they actually become available, sort of built into a combined conventional quantum sort of hybrid platform?
I think it's a very good question. Can I just also, so first and foremost, will they be in the same quantities? And the second one is how will they be accessible, I think. This is one thing. So if we could, Anthony, do you want to start? And then maybe Paul?
I remember a story about the CEO of IBM in like the 50s saying something, when it was all mainframe computers, he said something like, the world will only need 5 of these. We don't need computers on every desk. And so I'm loath to say that they won't be manufactured in large quantities, but there is a lot of work around networking quantum computers together and doing interesting concepts such as blind quantum computing, where you ask a question of the computer, and the computer could be located in another location, you know, in a data center. The data center does not know what the question is. It's encrypted somehow, but it can provide an answer and send it back to the user, and then the user can decrypt it without the owner of the data center ever being able to access that information. So it's kind of a different model. It's a different business to many other ways we think of as computing. And there's also a lot of really interesting work that you alluded to about co-locating data centers with quantum computers. So, you can imagine an AI data center or some other data center needs to constantly be optimized to cope with the number of access requests to it. And a quantum computer may be a good way of distributing that resource across the classical data center.
Paul?
I'll answer your first question. Sorry, your second question first, which is: will quantum computers be delivered as hybrid classical quantum? I think the answer is yes. In the most cases, we're seeing emerging algorithms. Quite a few of them seem to be developing with a mixture of, say, AI and quantum in a workflow. So you might use, there are different variants. You might use a quantum computer to optimize some elements to go into an AI model to simplify that, or vice versa. You might use an AI system to simplify a problem to the point where it works with a quantum computer, and then there's a workflow there. And so that's probably the way that it will be deployed in scale, and so as a hybrid system. And there's a sort of thought that maybe the way that the architecture might work out is that a computing environment might have a general CPU, and it might have an AI CPU, a GPU, or something like that, and it might have a quantum card, a quantum QPU sitting beside it. So then the question is, like, your question of scale is kind of like, if that's the model, then you could end up with them very highly scaled, but not necessarily as a whole computer, but you have to have those. Currently, quantum computers, you get superconducting ones, they tend to have to be in fridges, very big cold things. They're pretty bulky. But there are lots of other ways of building quantum computers that don't require that can fit in a normal data center. And the UK is probably pretty good, particularly at photonic ones, which tend to be smaller. So you might be able to get them kind of like smaller units that can be deployed around the network. So will quantum computers only be in data centers, or will they be distributed? I think that the technology is coming along which will allow them to be smaller so that they can be distributed. So you could have a reasonably large number. But I think there's something that we've not really touched on so much so far, is that it's not just the hardware. You need to think about the whole stack. In order to get quantum computers to be useful, and I think useful is better than advantage and all of those kind of things. In order for it to be useful, you need to have an application, something that someone can code, and you need to have some algorithms, you need to have the whole software stack that works quite smoothly. And then how that sort of develops with AI, classical compute and all of that, I think still has to be worked through, but there's a lot of work going on right now with, there are some companies that are focusing just on algorithms, some focusing just on the kind of middleware, and some focusing just on the interfaces, just to try and get all of those. And all of that needs to be solved in a way that then quantum computer can be used at scale. But the hardware, I'm optimistic there'll be a lot of it. I don't know exactly where it will be, and some will be cloud-based, and some I think will be distributed. But this is the opportunity I think the UK and Wales has, hopefully, because if it is photonic systems, then it probably does. And as you distribute the computers around, you'll need optical systems to connect them all together, which is why BT is particularly interested in it. And then that sort of falls into areas where the UK has some strengths and can really add some value.
Thank you. Any more who want to answer? Okay. Do you? Sorry? No? Okay, fine. Thanks. Any more questions from the audience? Oh, we got a few. Okay. So why don't we go? Okay, we got two more than there as well. Okay, good. Yeah.
It's a really good talk so far. Thank you so much for everything you said. My question is quantum a paradigm shift, or is it only going to be used to solve today's problems like AI and machine learning does?
Right. Who wants to go? Paul, do you want to go for it?
Do I? Not particularly. Is it a paradigm shift? I like to say it's a paradigm shift because that makes it sound like everyone should get behind it and do some stuff. So that's generally what I would say. Will it solve problems like AI and machine learning? It's like that means. AI is a paradigm shift as well. So I'd say if it's like AI, then that's pretty pretty impactful. It might not be as impactful as AI, but I think we'll have to wait and see because at this stage we're just at very early. But as you were saying earlier on, the things that have been announced about it being better are only really for toy problems. They're for things that are not really of any relevance. So at this stage, we don't know. It should be able to solve some problems that are impossible to solve in other means. For example, fluid dynamics. You still have to put things inside an air tunnel to test them, which seems slightly odd at this stage, but because you can't solve it with a classical computer, it just doesn't. But a quantum computer should be able to, when they're at the right scale. Will they get to the right scale, as you're talking about, this scale that you need? Will they get to that? I don't know, but if they're at the right scale, they should be able to solve that problem, and then you can design things intentionally as against try it out and experiment. So what will that lead to in terms of a paradigm shift? I don't know, but it's definitely different.
I think one of the things to bear in mind with all of this is if you start to look at some of the companies who are interested in using these computers. So obviously I talked about why someone like BT is interested in it, someone like the military or the police force are interested in it, but also we're seeing companies like there's a company in Oxford which works on fission. Fission? That's the right one. No, fusion is the one that we want. Fusion. So obviously, if we can solve that, right, if we can solve the fusion problem, that has real implications for green energy, for our climate, for climate change, things like that. Then there's other problems where people are very interested in the applications of these things. So I think some of the problems that could be solved if we end up with a useful quantum computer that's programmable to these problems, it could really change a lot for the entire world. But it is that question of when do we arrive at that useful quantum computer. The concern that we have within BT is that we knew that generative AI was coming, and then one morning we woke up and ChatGPT was there, and then the world changed, and we had to rethink education, we had to rethink all of these things. The concern that we have within BT is that there are players who are in the quantum space, who we know who are working in the quantum space, who are suspiciously silent about how much, and when we're talking quantum computing at this scale, we're talking state actors, right? We're talking different countries. Our concern within the space that I work in within BT is what happens on the day that we wake up and someone has broken their RSA cryptography, because then it's too late, right? You can't, to then deploy all the technologies that you need to protect yourself takes months. So our concern is that we don't want our customers waiting until the morning that we wake up and that paradigm shift has happened. We need to be prepared for that happening before it happens. So we can't be playing catch up.
Okay. Thank you. It's 2 more minutes we got. I know there are 2 questions.
Time for one more question.
But yeah, I was wondering if both ask a question at the same time, we can see what answers come. If that's okay?
I wanted to pick up on Anthony's point about press stories and how hard they can be and how misleading they can be. So I wanted to ask the panel about which stories around quantum technology have cut through to the popular press and been reported accurately.
And what is the next question? And see, and then, if you can combine, in front of you, sorry. Yep.
Lots and lots of questions, but I'll confine myself to one given the time limits. If you could say a little bit more about the applications of quantum to networks, that would be really interesting.
Okay, maybe that's a special one later on.
Yeah, I was about to say, if you want to just come up
Yeah.
afterwards and we'll have a chat.
Okay, yeah. And just with the question about what is, what was exactly the hype, what are real stories and what are...
I'll give you some context.
Yeah.
Mm-hmm. I know how hard it can be, so can we ever tell the public the real story about it?
So I think there is, maybe I was a bit negative. On a positive note, there has been real progress in the last 5 years, and that is due to the fact there is just a wall of money being thrown at this, not just by Google, Microsoft and IBM, but also by states. No one said China. Yeah, but I mean, the amount of money that the big tech firms have thrown at this is rumored to be insignificant compared to what China is spending on quantum technology. The level they're at is absolutely astonishing, and it's come in the last 10 years. You know, we talk about our network in the UK between BT's offices in Ipswich and London and Slough and Cambridge. That's the UK network. In the Chinese network, it's, I think, 8,000 kilometers or 8,000 miles. Yeah. And they've got the satellite. They had a quantum satellite up, which surprised everybody, I think it's fair to say. It's like a Sputnik moment for quantum communication. And in terms of computing, yeah, also extraordinary progress. It's really positive, and I think, although I don't know the exact answer to your question, I think there's a lot to look forward to. I think it's a very fast-paced and exciting time for quantum technology, changing how we think about nature, information, and how we think about the IT world and how things operate.
Yeah. Okay. Thank you very much. I think this is, sorry, we're at the end. It's now 4:02. So thank you for the panel, for attending. Thanks for being here and listening to us. Yeah. And with that, I would like to close.